So I'm very happy to be here, and I want to thank the organizers for the invitation. So I want to tell you about the conjectures that I think most of you are now vaguely familiar with, which I am willing to agree at least are rather stark. So, taking the brilliant idea that Brian had, I'm going to cut to the chase just in case. And so, let me give you the various versions of what the conjecture looks like. So, those of you that can't see it from this side, you'll have your revenge at some point. So, the general situation, it's kind of faint. So let's start down here. Oops. No, we can't have that. The general situation is that I'm interested in the first non-vanishing derivative of an Artin-L series at s equals 0. And the value of it is going to be somehow related to a piece of the regulator. And it's in that general formulation, it's extraordinarily nebulous, and I don't think anybody has ever made it less nebulous. However, it gets interesting in the case of abelian extensions, and in particular, it gets extraordinarily interesting in the case of abelian extensions which allow L functions with first-order zeros at 0. And so that's where the heart of the conjectures are. Even though if you have a 0th order 0 and you want to deal with it, you can artificially turn it into a first-order 0 by deleting an appropriate Euler factor. And so various things like Brumer's conjectures have become incorporated. There's also p-adic cases for which the conjecture seems to work equally nicely also, but they're not my fault, so you'll have to ask Dick. Okay, so I've got capital K over little k, which is a class field. The conductor is got a finite part, call it F, and then the infinite primes I'll lump into F infinity. So this is a typical situation. And then there's some sort of Ray class group, or in general, actually, sort of a generalized one. It's a quotient group, really. But think of it as simply the whole Ray class group, if you want. And I've got this class field that corresponds to it. And it corresponds to it via, well, in various ways. But the Galois group in particular is isomorphic to this group. And an explicit isomorphism is the Artin reciprocity map. Even though sometimes there's two versions of what the Artin reciprocity map says. Okay, so I take a character chi of this group, and if I put an ideal after L of S chi, what this means is that I throw out all of the Euler p factors that have anything to do with F. This is one of the interesting features of the conjecture, which slowly evolved over time, and that is that the imprimitive form of some of these things is very relevant, more relevant than the primitive form for the uniform versions of the conjectures. So I want to suppose that for all of these chi's, that L of 0 chi is 0. And then I want to start talking about the first derivatives of all of these things. And the first stage of the conjectures is a very nice conjecture, namely that these are all sums over the group elements of chi of G, log of a normalized valuation of a particular number epsilon from K, where the normalized valuation is the usual absolute value if it's real and absolute value squared if it's complex. And in front is this wonderful C chi, which allows me to guarantee you'll never disprove it. And in fact, if I allow it to be complex, you can't conceivably disprove it. But the typical conjecture makes it at least algebraic. But still, since it's dense, you'll never touch it. Okay, so that was the very preliminary stages. The preliminary stages go back into the 70s, But we'll get into the timetables a little bit later. So the next stage is to try to do some meaningful calculations with this thing. And in beginning the meaningful calculations, the next stage tells you what C chi is. And with the imminent primitive versions of the L functions, C chi is uniformly -1 over W, where W is the number of roots of unity in capital K. There's no more fudge factors. Oops. And to make it even more amusing, why the minus sign? Because with the minus sign, epsilon turns out to be, well, conjecturally, an algebraic integer in capital K. Okay, so this is starting to get interesting. For instance, with the trivial character, when you plug into this, you're learning about the norm of epsilon down to little k. Okay, the final stage evolved a little bit later. It evolved sort of between 1975 and 1980. The last version of my papers so far was published in Advances in Math in 1980, volume 30-something or other. And that is this extra part. Well, I don't need this anymore. The extra part says that when I adjoin the wth root of epsilon to capital K, I still have an abelian extension over little k. This is the most amazing feature of it to quite a few people. Some combination of stages 2 and 3 are what's now called the over Z conjectures. And there's absolutely nothing left to the imagination in the over Z conjectures. Okay, so let me tell you, to continue the final chase, what is known. First of all, there are 3 cases that are completely proved in this exactly. Is this focusable? Yeah. Okay. So first of all, it's proved when the ground field is the rational numbers. Second of all, it's proved when the ground field is complex quadratic. Third of all, it's proved when capital K is simply a quadratic extension of little k. Okay. What are some of the consequences, which are less obvious? First of all the conjugates of J are actually, of epsilon, are actually associates in capital K. This is sort of morally what you would expect, because this is supposed to be a piece of the regulator. And so I shouldn't even see something that isn't a unit. But if you have something that's all associates, since the chi values for a non-trivial chi has 1 degree of freedom, you can add anything to it, and all of the logarithms will not change anything. I have inside the logs really ratios of these epsilons, and then they're units. So this is a nice feature that they all are associates. Okay, epsilon is also a unit outside of F in all cases. Furthermore, when K is not Q or complex quadratic, epsilon is actually a unit. Okay, that means that numbers 1 and 2 are slightly cheating. So in the unproved cases, epsilon turns out to be a unit provably, mainly because one calculates from over there its norm and finds that its norm is 1. Or its norm is absolute value 1 anyway. And so its norm is 1, being an integer. And so it's a unit. In the other 2 cases, since it's proved, you just look at what you proved, and lo and behold, they're associates, and they're units outside F. So that's sort of cheating, but this is a nice way of phrasing it. Okay. Furthermore, when our ground field is real, then the class field, I didn't get into this, but when we're doing this numerically, we're talking about explicit embeddings of these things into the complex numbers. And when the ground field is real, the right embedding of everything is that the upper field is real as well. And so the epsilons and their conjugates are all real. They're all the same field. But in addition, they all have the same sign. And the reason they all have the same sign is you change the sign of one of them, which doesn't change the conjecture at all, having absolute values. and then the wth root of that, w being 2, is automatically real. And since all of the k of 1 over epsilon to the 1 over w's are the same field, all of these square roots are real, and so they're all positive as well. So in short, when k is real, you can take all of these epsilon applied to g's positive, and the absolute values go away in that case. And the conjectures then tell you, essentially in the calculations numerically, what the conjugates of all these epsilons are, or at least the conjugates over little k. For a real ground field, they also tell you, in the interesting cases, what the other half are in absolute value. And as a result, you can numerically calculate the coefficients of the defining equation over Q. And so finally, I'll put up this consequence that if you're dealing with a real field, you can actually crank out the algebraic defining equation for epsilon without any doubt. There's no ambiguity. You have enough digits and you'll get the defining equation and you'll know that this is it and there's no other possibility. And so either at that point it works or it doesn't. And so in particular, there's absolutely no question that you can disprove this conjecture with a single example. And it'll be convincing that the conjecture is in need of modification. The modification, I suppose, would be first you erase stage 3, and then you erase stage 2, and then you can't touch me anymore. Okay. I wanted to go into the history, but I should say at this point, I think an infinitesimal amount, having heard the first 2 talks about examples. So for instance, you could take little k equals q square root of minus 139 with class number 3. And you could take then simply the Hilbert class field thereof, and then there's a Galois group of order 3, and there's 3 L functions. But one of the L functions, the zeta function of the field itself, is got a value at 0, which is non-zero. Namely, it's minus the class number divided by the number of roots of unity in the field. Okay, this is bad. I want values all 0. Experience says that when something interesting happens at some derivative, then the next derivative has unknown transcendental junk in it. But if you artificially wipe out the lead term by raising the order of 0, 1, then suddenly the next term starts making sense again. So in this case, we'll take as our conductor, there's no more infinite prime problems in complex quadratic fields, we'll take our interesting conductor to be generated, it's a principal ideal of norm 37. And Dick gave you a number. Okay, and then zeta k of 0 and this prime of norm 37 now has raised the order of the 0. And so it becomes minus 3/2 times log of the absolute value of alpha squared, otherwise known as 37. Okay, so now I've got myself 3 L functions. All the class group L functions, but I've got 3 L prime of 0, chi's, and P37. And so I'm going to be minus 1. The class field has got 2 roots of unity. The summation over the 3 classes of G, of chi of G, log, double bar, my number epsilon circle G. Okay, so what the conjecture says in short. But now, the non-trivial chi's already had first order zeros, and since I'm dealing with a principal alpha, I've turned them into second order zeros. And so I've got only one interesting value between these 3 things for the trivial character, and therefore all 3 of these are equal. Their norm is 37. They're associated to the ideal itself. And furthermore, things are equal. In short, this number is not in the Hilbert class field. It's in the ground field. And it's nothing more than alpha itself. And that produces the 3, because the class number is 3, when you take the norm. So this is Dick's example. It turns out, of course, that when you're dealing with the class field, you come up with, inside the logarithms, combinations of eta functions at nice points. And so it's exactly the example you just saw. When you're in complex quadratic fields, but you're not dealing with things that are class fields or ring class fields, then it's not Kroneker's first limit formula that's inside, it's Kroneker's second limit formula, which is more interesting. Okay, one other quick statement, which is that if I have this tower of fields, K to capital K, and then I've got some sort of bigger field, well, let's see. Whatever, I've forgotten how to write a capital K, in which the same primes are in the conductor of capital K as in little k, then there's no extra damage in the Euler p factors, and so the L functions of this, the primitive L functions of this are talking about the primitive L functions of this, for instance. And so in the conjecture, if you group things, you see a relative norm of the unit here down to here, which in absolute value is the same. And then you have to unwind for complex quadratic fields and see that what's inside the logarithms are the same. I'm not sure anybody has ever completely written that up or not. I haven't followed it. It's clear that it well, let me say, deserves to be the case. To me, it's been obvious for 25 years that this is the case. But I have to admit, I never bothered to work out the 12th roots of unity and verify it. But you get these relative norms, and I believe that people that talk about Euler systems should take note of the relevance to the conjectures. Okay, so that takes care of the end game. It also takes care of almost half my talk, so it's a good thing I got to it. Okay, so I was going to talk about history from 1966 to 1980, but after Brian's talk, I think I have to go back to 1963. So I was amazed to discover, I never knew this before, that I came across Heegner's paper before Brian did. So there was this long period of time after Heegner's paper appeared where, well, I gather that people tried to invite him to give talks about it and that he declined. He just wasn't interested in doing it. But by the time I was a graduate student, it was essentially totally forgotten. The popular claim was that it relied on an unproved conjecture of Weber. In Brian's notation, I guess it would be the value of sigma to the first. In Weber's notation, this was one of the 3 Schläfli F functions at another point at square root of d. And Weber claimed to have proved that the square of this number was in the class field. I'm not sure very many people have read Weber's proof of it, because via the reciprocity laws nowadays, it's a cinch. But nevertheless, I think Weber's proof was wrong, even though Weber's methods, you could adopt them. Weber's methods were an art form. You find 2 things that you can prove have nice coefficients whose GCD has exactly the one thing in interest that you're interested in, and then it has values in the same field. It's an extraordinary method, quote unquote, but it's the finding of the 2 things. And I'd swear Weber did not find 2 things that worked in the case of this one. But you could use his methods, which were the only methods I knew at that time, later on, and prove that Weber was right. Anyway, so Heegner, there was no question, though, that Weber never claimed to prove the value of sigma. And the powers that be back at that time decided that this was what Heegner's proof of the class number problem, that there's only 9 complex quadratic fields of class number 1, relied on. So I was a graduate student in the early 60s at Berkeley. Lehmer was my advisor. I'd learned of the class number 1 conjecture by a reading course when I was an undergraduate from Hardy and Wright. And to me, reading that book, it was obvious that you could prove this. And mercifully, no one told me that I was an idiot. And so I started working on it as an undergraduate. And when I got to Berkeley, Lamer had thought about it and proved the best existing numerical bound that you'd have to go out to 5 times 10 to the 9th in absolute value of the discriminant before you could possibly find a 10th. And so I marched off to Berkeley. The person that I did the reading from was at Caltech was Morgan Ward, and I'll get back to him in a second. Okay, so there was no hint that this problem had been proved mercifully, or I wouldn't have been working on it. And so I started working on it, and around 1962, I started reading math reviews. I decided that I would find everything in math reviews that had anything to do with this problem. It was a good thing for graduate students to do, even though I must admit that now it would be a much more daunting task than it was in 1960. But by 1963, I was essentially through the complete set of math reviews, skipping everything that looked of no interest whatsoever. In particular, I skipped the review of Heegner's paper because at the beginning it was talking about solutions to Diophantine equations. And it turned out that the reviewer of this paper was Morgan Ward, which I find rather interesting because as I discovered in 1963, as I was getting my thesis results, as I discovered in 1963, the last line of Ward's review says that Heegner also proves there are only 9 complex quadratic fields of class number 1. Since my thesis was pushing out to 10 to the 10 to the 7th instead of 10 to the 9th, this called my graduation into doubt. I hadn't written it up yet. I wasn't going to graduate in 63, but I was aiming for 64. So I went to Lamer, somewhat disturbed, and he was going to a conference in Colorado in 1963, in which various high muckety-mucks would be there. I don't think I'll name one of them. But I'm sure I know who it must have been that reassured Lamer at the conference that no, Heegner was all wrong. So Lamer asked them, and once again, he came back with the news, no, I didn't have to worry about Heegner. Heegner was mercifully, had nothing good to say about the subject. And it was relied on an unproved conjecture of Weber. Okay, so that allowed me to graduate. So I'm quite thankful for this. But somebody, for quite a few years, performed a major disservice to mathematics. So in 1966, I actually worked out the proof in the summer of 66. We finished it in August of 66, at exactly the same time, within a week or so, as far as we can tell, of each other, that Baker finished his linear forms and logarithms version of the same thing. Baker was lucky. He got his proof into the last issue of 1966 Mathematica, whereas I got my proof only into the first issue of 1967's Michigan Math Journal. But they're simultaneously, essentially. And as far as I know, I am the first person to have looked at Heegner since the initial times. And I didn't understand a word of it, of course, for 2 reasons. The least difficult reason was that it was in German, and my German was abominable. The most difficult reason was that that's a hard paper to read. It bounces back and forth between one thing and another. And there's no question in the course of the paper that he's talking about Weber's conjecture. But there's also no question once you unravel it that he's not using it in the slightest for class number 1. What he is using for class number 1 is the value of sigma squared being in the class field. And of course, I didn't even know what a class field was. Sorry to say, this is one of my teachers here who probably presumed that I did know what a class field was. But anyway, So I had great difficulty, but I could sort of figure out what Heegner was doing and how Heegner was deriving his Diophantine equations. And I sort of sketched it out in the paper that he's doing this and this and this. But I wasn't going to touch a value of a modular function or a modular function for anything, given that the popular belief was that he was doing illegal things in modular function values. And so my paper is totally elementary. But in disguise, there's a modular function in it. And one is talking about, in particular, values of certain types of L functions. Okay. So I take a quadratic form whose discriminant is D, which is less than 0, and let it be the field discriminant of a quadratic field. And I have an Epstein zeta function, zeta of SQ, which is the summation of the quadratic form values to the minus S power. In disguise, this is nothing more than, well, in the class number 1 case, which I was exclusively interested in those days, this is nothing more than the zeta function of the quadratic field times the number of roots of unity in the ground field, which is usually 2. But I thought of it in terms of quadratic form values, and there were all sorts of elementary theorems in Landau telling you how this was Riemann zeta times L of S chi, a Dirichlet L function with a Kronecker symbol. And here's the corresponding expression where little w is the number of roots of unity when the class number is 1. And this is the corresponding Kronecker symbol. It's the corresponding character. Okay. Going into the theorem were some modified things where you take a character where f is also the discriminant of a quadratic field, and you toss in the character value, chi sub f, evaluated at the quadratic form value, times q of mn to the minus s. Okay. That's sort of a shocking thing to look at. Even those of you that are in the know realize this is nothing more than an L function on the quadratic field. No, I didn't know any of that, but the elementary theory in the class number 1 case said that this thing decomposed just like the zeta function did into a product of these two things. And this combination of things already goes back to Heilbronn in the 1930s. And in particular, Heilbronn found a fascinating expansion of this when f is a prime number, which is rapidly converging. It also had one extra logarithm in the linear forms and logarithms than was necessary, because if one had looked at f equals 12, the linear forms and logarithms, people would have done the class number 1 problem in 1948, because it would have turned into 2 logarithms instead of 3 logarithms. But I'm the first person to ever do the expansion for a non-prime value of f and discover that one term disappeared. It's quite amazing. So I lucked out again. But anyway, this got me interested in general into questions. What does the value of this look like in the non-class number 1 setting? I had learned either late in my graduate career or very shortly thereafter that an Epstein zeta function all by its lonesome self had an analytic continuation. I should have known that, but I didn't. And so having been burnt by that, because lots of my attempted proofs relied on it not being able to do so or things like this, and I discovered that it had analytic continuations exactly of the sort that would wipe me out every time. But then I began to think, okay, and if that worked, then why shouldn't this have nice values as well? And so this is what got me into the conjectures, was wanting to know what the algebraic nature of this looked like in the non-class number 1 setting. And my initial questions in part 1 in particular were about L functions of quadratic forms. Okay. I proved that you came up with a log of something or other inside the thing. It was a Kronecker's, well, ultimately, thanks to Siegel telling me, it was Kronecker's first limit formula rather than the second limit formula, and it was much more malleable. And I proved that the 48th power was in a nice class field of something that already should have been in the class field. So this also incidentally got me interested in the question of whether you could take roots, because in all the numerical examples I could put my hands on, namely class number 1 and 2, I could calculate that I didn't need that extra 48. Okay. So, well, Heegner was corrected in short order. 3 papers appeared. They were worked out, as far as I know, roughly the same time, but they appeared probably in 3 different years, of which mine was the last because it was in volume 1, number 1 of Journal of Number Theory that didn't bother to start up until 1969. But in the summer of 1967, I painfully went through Weber, which is an interesting exercise. I recommend it to you if you've got a summer to spare. It's encyclopedic and it's extraordinarily hard to read. And he would have been infinitely better off with the reciprocity law that unfortunately didn't come into existence until Shimura. At which point all of his special values are homework exercises. So the 3 corrections of Heegner, so-called, are one of mine, one of Doering, and one of Bryan's. And Bryan went further and proved Weber's conjecture for good measure. And it's the first proof of the conjecture that I know of. My method would not. I never found the art form combination that would allow me to take the extra step down and find a GCD. It would be fun for historical reasons, but only that. And Doering essentially just outlined the proof and didn't say anything about whether sigma, about Weber's proof of sigma squared. Oh yeah. Siegel wrote a fascinating paper in 1968. He didn't correct Heegner, but he wrote a paper in 1968 on a theorem of Stark's, approximately, which I'm honored. And if you have your name in a paper of Siegel, and it isn't simply because it's a strong theorem. And he put Kroneker's limit formula into it. I knew what Kroneker's limit formula was because I'd read Weber. But if you want to see the worst proof of Kroneker's limit formula in the history of the universe, I recommend reading Weber's proof. Because it is extraordinary what he does to avoid the Poisson summation formula. He has the product of 2 gamma functions. He has the norm of something, of course, complex quadratic. So you take one factor and it goes to one gamma function, one factor goes to another, and so you turn it into a double integral. And then, of course, once you've got a double integral, you're required to do some variable changes. And so you do some variable changes, and then you do some more variable changes, and then you do some more variable changes, then you do some more variable changes, then you do some more variable changes. Okay, after some pages of that, you then expand the whole mess into a Fourier series, so you don't have to say Poisson. You move over sideways, and eventually you come up to inside the double integral, you've applied the Poisson summation formulas. And now you start integrating the whole mess. And you integrate, and you integrate, and you integrate, and you integrate, and you integrate. And at the very end is the Kroneker limit formula. Okay, now if instead, of course, if you said Poisson summation formula down here, this part would be easier. Well, it turns out that if you had set it here, you could have gone straight here. And then if you had set it here, you could have gone straight here. And then if you'd set it here, you could have gone straight here. And if you'd done it at the top, you would have had the Poisson summation formula without getting through any of this. Not the Poisson, but the Kroneker limit formula. I knew the problem involved Kroneker's second limit formula. And it wasn't until I learned that the first limit formula was involved in this that I was able to start efficiently doing the expansions. And so it wasn't until Siegel's paper that I realized that these things were all expressible in terms of the first limit formula, which is much less painful. It involves doing the calculations in ring class fields rather than array class fields that are much bigger. Okay, so I guess we're ready for over here. Okay, so let's see how far we can get now. So in general, I've got the zeta function of a number field. I'm interested in values of that sort of L function, but it gradually grew into getting vaguely interested in L functions in general. And so here's the zeta function of a number field. The zeta function of Q is the Riemann zeta function. There's a functional equation of S goes to 1 minus S. There's a residue of the zeta function which involves practically all of the invariants of the field, of which the class number and the regulator is certainly the most interesting part, and all the rest is sort of sitting there, unfortunately, including powers of pi and various things. When you flip by the functional equation to S equals 0, it turns out that all of the junk goes away. And you simply get minus the class number times the regulator divided by the number of roots of the unity. One of these W should have been a little w or a capital W. They're the same W. So this is rather interesting. And also, actually, this one works if you're dealing with S integers as well, and you crank out the corresponding zeta function. The rank goes up. You'll get the regulator, the class number, the whole works. It's the same formula, exactly. Whereas here, you just get some extra miserable Euler factors that don't look like they've got much to do with H and R. And you can prove it directly, but this is not the time. Okay, so I was visiting Göttingen in 1970. Actually, I had a Sloan Fellowship, and so I spent 10 months there. And I had the office right across the hall from Siegel's office. And Siegel came in every day, and every morning I would go and talk to him. So in spite of the stories that one hears about Siegel, in my case, he was extraordinarily kind and non-temperamental, even though I noticed that the people in Göttingen were terrified of him, absolutely terrified. And if we had him over to our house for dinner, they were just, how can you invite him to your house? And of course, he happily came. He had some quirks. And of course, there were stories galore about him. The one time I noticed any hint of the temper that he was rumored to have had was when I went into his office one day and told him that I thought that L functions of real quadratic fields ought to have interesting values of derivatives at s equals 0, or interesting values at s equals 1. Because I was beginning to organize the vaguest forms of the conjectures. And amazingly, it's sort of like a well-known story of Hilbert. Siegel got very annoyed at that. And he said that this is absurd. And the reason it's absurd is it would mean you could factor the regulator. This is very interesting because, as I learned the next day when I came back with numerical examples of factoring regulators, that you just do by hand. You play with the determinants and you split it into pieces. I didn't know anything about the theory to come. I went into his office and showed him this, and then he remembered Brouwer's papers from the 40s. He'd simply forgotten about them. So he told me about Brouwer's papers, and it was Siegel that introduced me to group determinants. And he learned the theory of representation theory via the original methods where you treat the group determinant and deduce representation theory. Whereas now you know representation theory and treat the group determinant. And so I'm extraordinarily indebted to him for that. Because I didn't know anything about representation theory. I'd never seen a group determinant. So just so you can't make the same claim, suppose I've got a field, capital K, over little k that's normal. Its Galois group is G k over k. I've got an irreducible character, not necessarily first degree. So the zeta function then factors according to the Artin methods into a product over the characters, irreducible characters of the group of the various Artin L functions raised to the degree of the character. The regulator factors also. For illustrative purposes, I'll take the case where the ground field is Q, and I'll tell you what a group determinant is. So to each element of the group, I'll introduce a variable, x sub element of group. And then I'll create a order of group by order of group matrix, x sub I inverse j, or the entries, the ij entry, where I is a group element and the j is a group element. And it's the determinant of this thing that will be the group determinant. Okay, I split this into a sum over the group elements of the x sub g's times a of g, where a g is now a 0, 1 matrix. Okay, and what is the 0, 1 matrix? Well, it's got entries ij of g, and the ij entry of such a thing is 1 when I inverse j is equal to g. And that way, my original matrix is split up into this linear form of matrices with 0, 1 matrix coefficients. Okay. Now, if V is a column vector made up of the entries of G, then you work it out and you see that AG here is exactly, when it multiplies V on the right, is exactly V with G on the left. Oops, the other way around. Well, interchanging right and left, VG equals A of G times V. Okay. The result is that what you have here is simply a representation. This is the right regular representation, except for those people for which it's the left regular representation. Okay. So, in particular, you take a second element H, say on the right-hand side, multiply it in, and then A of G comes past first, and there's an H here, then A of H comes past second, and so you see, because this determines the matrices, that A of G times A of H is A of GH, and so this is a representation. And as I say, it's the right regular representation. Okay, and so this thing splits into pieces according to irreducible pieces according to representation theory. And so the group determinant, which is the determinant of the whole thing, factors into nice pieces according to representation theory. The special case of a cyclic group is fairly well known to a lot of people. It's a circulant matrix. And that's a reasonably well-known case, but this is the general situation. Okay, I'm going to illustrate the case where capital K is real because it makes my XGs a little bit simpler. It gets closer to the regulator. And I'm going to introduce something that's called a Minkowski unit. And in the case of a real field, it's a unit of capital K such that the only relation between it and all its conjugates is the norm relation. Okay, and now I'll set the xg is equal to log of the absolute value of the g conjugate, and then plus 1. The plus 1 is to deal with the trivial character, and it's going to lower the size of my determinant by 1. In the case of a complex field, I have to do something extra, and for half of the epsilon g's, you add an extra, say 1/2 or something, and for the other half, the complex conjugate ones, you add an extra minus 1/2, and that allows you to sort of cut your matrix size in half at the end. If you knew how to factor the class number better, you use 1/2, you didn't use things related to class numbers. But anyway, so this is the only relation. So now, I want to take a piece of my group determinant with these xg's, and if rho is an irreducible representation, then when I add all the xg's together, the logs of the epsilons, I pick up the 1 with the trivial character, if it's rho 1. But on the other hand, thanks to the plus 1s, they all add together and I get the order of the group. And so that factor is sort of nice. At the same time, that factor in the big giant group determinant matrix, if you picture adding all the columns together, you get nothing but order of group in the back column. You pull out that, you've got all 1s here, you now get rid of all the remaining ones, you add all the rows, you get order of group down here again and a bunch of zeros, and now you've gotten a determinant one size smaller, which is a regulator matrix. So we're putting together, we're factoring the regulator. And in the other cases, the row of g's, the sum of the row of g's for a non-trivial irreducible representation adds to 0. This is the Schur relations. And so the 1s disappear, and the sum of the xg row of g's is simply the sum of the log absolute value of epsilon's row. And so I'm factoring my regulator into pieces that are relevant. Okay. In the generalization to other ground fields, in general, it's convenient to use something called Artin units, a system of Artin units. Or if you want to deal with S integers, you have to introduce a system of Artin units. And then it gives you an idea of what factors of the regulator look like, at least. And then you want to start taking things that look like this and matching them against the L function derivatives. Okay, so this was the very beginnings. Okay. So I published part 1 about values of quadratic, the original L of S chi q's, in 1970, I think, approximately. And I gave a talk at the International Congress where I put forward the most vague form of the conjecture with fudge constants galore, so it's obviously true. Because I'll just change my constant if you find a counterexample. There's no hint as to what the constants should be. Okay, we'll skip one part of it. So now I want to go to the next stage. I was still phrasing this in terms of s equals 1. S equals 1, s equals 0, they're the same, more or less. So I want to tell you next what led me to s equals 0. So suppose you take a Dirichlet L function, L of s chi, the most basic example. And I want to evaluate L of 1 chi. There sometimes should be a p infinity there, but we'll ignore that. In Dirichlet's notations, there were no p infinities. So here's the sum. And I want to find L of 1 chi. So Dirichlet decided that the way to do this is to Fourier analyze chi. He didn't say it that way. But chi is periodic, and so you expand it in the finite Fourier series. And so you get a summation from 0 to f minus 1 of c sub chi of a, e to the 2 pi I a n over f, where the c sub chi's are, who cares? Well, Dirichlet cared. But anyway, it looks like this. The a equals 0 term is not there. I'll say that now, for interesting characters, because the 0th term has coefficient 0 in the Fourier series. The orthogonality relations wipe out the 0th term of the Fourier series. Okay. Furthermore, if chi of minus 1 is plus 1, then c sub chi of a is c sub chi of minus a. And if chi of minus 1 is minus 1, then c sub chi of a is minus c sub chi of minus a, because of the uniqueness of all this stuff and the fact that the characters have the right. Okay, so let me first start. I'm going to plug in to the Dirichlet series and evaluate at 1 the corresponding thing. And you get a summation of c sub chi of a e to the 2 pi I a n over f times 1 over n. And then I'm going to interchange the order of summation, which is mandatory whenever you have a double series. And then I'm left with this, summing on the a outside and summing on the n's inside. I don't think I've ever seen an interesting example where a double series was introduced and then the order of summation wasn't interchanged. That came from a single series. It'd be extraordinarily perverse. But anyway, so we do this. And this, of course, is a logarithm series. And since the a equals 0 term is irrelevant, I simply write it up. And this is Dirichlet's formula. Now, why is Dirichlet's formula so difficult to understand? Because Dirichlet told us what the c sub chi's are when chi is primitive. And when chi is primitive, the c sub chi's are essentially independent of chi. Or at least they're independent of a. They're chi bar of a is essentially, and nothing more, and that's the a dependence. And then the c sub chi's are Gaussian sums. They're a fudge factor that pull out completely and have no a dependence at all. But if chi is imprimitive, c sub chi is a nuisance. So this is not uniform across all chi's by any means, even though it's quite uniform for primitive chi's once you go through a lot more about primitive characters and Gaussian sums. Okay, when c sub chi of minus a is c sub chi of a, this is the case where you're talking about a real quadratic, or a real abelian extension in the class field theory version. Then you put together the a and minus a terms of this and sum it halfway up. And outside of f equals 2, there's no problem. When f equals 2, you've got to worry about what that top term means. But otherwise, the c sub chi of f over 2 is 0. Anyway, you get this, and here you recognize quickly that you're talking about 2 sine of pi a over f quantity squared. Okay, so you see a sign, and the reason for the 2 is, that's a good question. It happens. Okay. So there's several features of the ultimate conjecture there, but it's well hidden because there's this nebulous stuff here that has rather messy fudge constants. It's got a Gaussian sum in it, and then it's primitive characters only. So I want to look at the same thing at s equals 0. And whereas at s equals 0, here you analyze it at s equals 1, and you Fourier analyze it, you smear all the classes together. At s equals 0, all of these classes together on this side turns into one class on the s equals 0 side in the functional equations. And so s equals 0 actually is an infinitely pleasanter location to deal with. So you introduce a partial zeta function. This is the zeta function of a single class mod f. The sum over the things in the congruence class of A modulo F. And I'm going to be interested in the chi of minus 1 equals plus 1 case. So actually, a single class in the class field theory sense is the union of two of these congruence classes, the plus and minus A classes, which I'll write as zeta of S A F and zeta of S F minus A and F. Okay, so I'll go through this very rapidly. You can do it yourself once you know what to do. So I'm going to introduce an extra term of 2 times f to the minus s times zeta of s, and there on the very far right-hand side, you see it subtracted out again. Okay, so there's no harm there. The initial n equals 0 term, nf plus a to the minus s, that's the a to the minus s. And then the rest of the first series is n equals 1 to infinity nf plus a to the minus s. So far, so good. The nf minus a to the minus s starting at n equals 1 is equivalent to starting the other series at n equals 0 with an f minus a. So I've written this bracket this way. And the beautiful thing about this bracket is that it's smaller than you think it is. It's 2n smaller than you think it is. Because if you expand nf plus a to the minus s in the binomial theorem, you see the nf to the minus s twice, subtracted out. Then you see a minus s nf, et cetera, times a, and a minus s nf, et cetera, times minus a. And so those two terms cancel. And the next term in the series is an n to the minus s minus 2. So this summation grouped this way converges absolutely back to minus 1. And so in particular, you can play with it to your heart's content at 0. Okay. If I plug in s equals 0, you get 0. The brackets cancel out completely. Zeta of 0 is minus a half, and so those terms cancel. And so the individual partial things are 0, just like they ought to be. And so from my point of view of my conjectures, I'm interested in the first derivative. So I crank out the first derivative at s equals 0. And you come up with something like this just by differentiating term by term and then plugging in s equals 0. And you say something about absolute uniform convergence to justify it in the original series. And then you can do anything you want in complex variables. So you do that, and then you rearrange it. And to make a long story short, you see the infinite product for the sine function if you know that zeta prime of 0 is minus 1/2 log 2 pi. And if you don't know, you take the f equals 2 case of this, and you deduce that this is the right answer, because you know what the zeta function is with the 2 Euler factor wiped out. And then, because this is the right answer, I had the right value of zeta prime. Okay, but anyway, this is the way the conjecture looks. It's amazingly the way the conjecture looks. So what are the features of it? It's uniform for all of these partial zeta functions. It gives me the values of L prime of 0 chi for all of the chi's, and it does it whether it's primitive or imprimitive, as long as I delete, which I forgot to write down, the Euler F factors. And by its very nature, the epsilon is an algebraic integer, and by its very nature, it's a unit outside of F, and by its very nature, since it was squared from something else, the something else is also abelian, even though not in the ground field. Okay, so this is the k equals q case of the conjectures, essentially, completely proved, and it's totally elementary. The Kronecker limit formulas with some algebraic lemmas allow the same thing in complex quadratics. And the experiments with the real quadratic fields were ultimately what led me to prove the exact form over complex quadratics, because the real quadratic fields sort of gradually through these stages kept pinning down more and more as to what was happening and making clear that the imprimitive version was what was relevant in the numbers. And this is what led to the conjectures. And oh, one last word, I've got 1 more minute. The over z part. What led to the final square root theorem? Why the wth root? Where is the original conjecture? The original conjecture is, okay, here it is. Oops. So here's the original conjecture. I have this extra minus 1 over W summation. And examples say you're not going to improve on this in any way, shape, or form. Epsilon is not a Wth power. If I multiply all these things together, I see order of group number of W's in the denominator. And yet the final regulator formula for the zeta function says 1 over W times stuff in the numerator. So how am I going to get rid of those W's? There's got to be order of group minus 1 relations where things are Wth powers. What's the easiest conceivable way to make that happen? Epsilon to the 1 over W added to the ground field is a normal extension. The fact that the popular phrasing, actually, I've never said. My version, which is all I ever needed for theory, was that the upper field was at least normal and that the subgroup fixing script k to cap k was in the center of the other. But all examples say abelian. And certainly I'd be astounded if the conjecture were ultimately right in the original phrasing rather than the word abelian. So with this, you can then put together, you can pull out order of group minus 1 W's when you multiply the whole thing together. And that was the reason for the Wth root conjecture. And it also didn't hurt that it's true for rationals and complex quadratics. Well, as you know, my love for function fields is immense. And so, thank you.
Are there any questions or comments?
No counterexamples?
I have a question actually. Is there any reason why behavior s equals 0 is so much faster than s equals 1?
A lot of the extra fudge constants, of course, disappear completely. It's a much nicer thing.
But you have a philosophical justification, other than that you do the calculation.
I decided I had to make a choice in doing the original calculation. And it's because the Gaussian sums weren't there. That an individual partial zeta function was actually was going to give me the number, whereas it was some sort of average smear of the individual partial things at s equals 1 that's giving me the number. And for that reason, that's why I started looking at s equals 0. It's missing one thing that happens at s equals 1, and s equals 1 treats all characters, infinite primes, the same. You get a residue or value, as the case may be, independent of how many infinite primes you've got. And so you've got these on the real quadratic case, you've got the characters where you've got a quadratic form and logarithms of units probably, and linear forms and logarithms units, and values, numbers related to class numbers, all in the same formula. And there's nothing in the conjectures at s equals 0 that interrelates these things like that.
Are there any other remarks or questions?